This is the first video lesson for Level 2. We're going to be studying Chapter 2, Section 1, which is all about conditional statements. Here's a conditional statement. If a car battery is dead, then the car will not start. Well, first of all, this is a true statement, but this is a conditional statement because it is in the form of an if-then statement. So our first definition idea is that what is a conditional statement? An if-then statement, where the if is something that has to happen first, and the then is the result of that happening. So if a car battery is dead, we go out to a bunch of cars in the parking lot, 10 cars are there with batteries that work, then there's the 11th car, it has a battery that's dead. Now the condition has been met, so we can check. There's a then. If the car battery is dead, we can make the conclusion the car won't start. This is a if-then statement, called a conditional because it has a condition that must be met and a conclusion that happens as a result of that condition. Every conditional statement has two parts. It has a hypothesis, the part following the if. This is also known as the condition, what I just said. The car battery must be dead in order for us to have this conclusion. Then there's the conclusion, the part that is following the then. This is the result of the condition happening. So, from our previous example, a car battery is dead is the hypothesis. The conclusion is that car will not start. This is an example of a true conditional statement. In order to decide whether or not a conditional statement is true, we have to determine whether the conclusion will actually happen, but only if the condition has been met. Only if a car battery is dead, then we decide, does that mean the car won't start? If we have a car that's battery is not dead, this statement does not apply. So to check or determine the truth value of a conditional statement, once the condition is met, we determine whether the result is actually true. In the example above, like I said, we only consider cars with dead batteries. The condition has been met. We will not, or will those cars start? No. So therefore, this is a true statement. Notice it says, will those cars with a dead battery. Okay, here's another example. If a shape is a square, then it has four sides. True, because all squares, that's the condition, has to be a square. I'm holding a shape behind my back. I'm telling you it's a square. Can you conclude that it has four sides? Yes. Now let's look at the converse, and we're going to discuss what the converse is in just a second, but it means to reverse the statement. If a shape has four sides, then it's a square? Well, this is false, because not all shapes with four sides, that's our new condition, are squares. Well, then there must be a counterexample out there. There must be something that shows us four sides that's not a square. Well, this parallelogram is a counterexample. It meets the condition, it has four sides, but it fails the conclusion. That is how we show that a conditional statement is false. We make the condition happen and show that the conclusion is wrong. The condition has four sides, but it's not a square. So, this introduced us also to the converse of a conditional statement. The converse does not exist on its own. You must have a conditional statement first. Then, the converse of a conditional statement flips the hypothesis and the conclusion. The if becomes the then becomes the if. Just because a conditional statement was true doesn't mean the converse is true. We just saw this. If a figure is a square, it has four sides. True. If a figure has four sides, then it is a square. False. Counterexamples are what we use to prove things false. A counterexample is something that meets the condition but fails to reach the conclusion. On the previous page, the parallelogram was the counterexample. You only need one counterexample in order to prove a conditional statement false. You don't need lots of counterexamples. few counterexamples, just one. One counterexample means a statement is false. There is no sometimes. Conditional statements are either always true or you go to it is false. There's no in between. Okay, let's look at another example. Perpendicular lines intersect to form right angles. This looks like the definition of perpendicular. We're going to take this and put it into a conditional statement. We're going to write it in if-then form. Conditional. If two intersecting lines are perpendicular. So if the intersecting lines are perpendicular. Are we talking about parallel lines? No, they have to be intersecting. The other part of the condition is they have to be perpendicular. Then they intersect to form right angles. Well, true. That's what perpendicular lines do. That's what it says here. Now, the two lines are the subject of this. So when I write the converse, I leave the two lines in the if. I don't say if they. If two lines intersect to form right angles, this is now the conclusion, then they are perpendicular lines. Well, this is also true. If I tell you they're perpendicular, you know they form right angles. If I tell you they intersect to form right angles, you know they're perpendicular. The original and the converse are both always true. Well, then this is a good definition, because good definitions are reversible and always true. This is a good definition of perpendicular lines. One final example for today. An integer that ends in 0 is divisible by 5. This is a conjecture. Let's put the conjecture in if-then form. If an integer ends in 0, then it is divisible by 5. Okay, an integer ends in 0. 10, 20, 30, 40. Yeah, those are all divisible by 5. So we can say that this conjecture or this if-then statement currently is true. But now take a look at the converse. If an integer is divisible by 5, then it ends in 0. If an integer is divisible by 5, then it ends in 0. Is this a true statement? No, this is false. And if it's false, there must be a counterexample. You should already be thinking of a counterexample. You should be thinking, well, 25 is divisible by 5, meets the condition. Does 25 end in 0? No. My counterexample is 25. The number 25 is divisible by 5 and does not end in 0. I only need one counterexample, but I bet you can think of more. I bet you thought of one that might have been different than 25. 15, 35. Any number that ends in 5 would be a counterexample to this. But I only need to show one. That's it for Chapter 2, Section 1, Conditional Statements. Look for video number 2 for tomorrow.